For an Einstein solid with each of the following values of n and q, list all of the possible microstates, count them, and verify formula 29. Okay, so let's start with part A. We will do a table sort of like table 2.2 in your textbook. And here n stands for the number of oscillators and q stands for the energy units. And so in part A we have 3 oscillators and 4 energy units. Okay, and so I will make a table here. Oscillator, so this is oscillator 1, 2, 3, and we're gonna list the energies here. That is Q units. So we have 3 oscillators, we have 4, right? So okay, and so the way I would start this is so we have to have a total of 4. So if oscillator number 1 was carrying an energy of 1, oscillator number 2, it has to add up to 4, so this is 3. So we're doing part A. So this would have to be 3 and this would have to be 0. Or the other way around, if oscillator number 1 had 1, 3 could be the third oscillator and 0 the second. Or the first could be 0 and then I could vary the other two, so I could have 3 here and 1 here, or 1 here and 3 there. So you can see we're gonna have to do all the combinations that go along like this, such that the total number of energy in every row is 4, and we have 3 different oscillators. And okay, so we have now we could get 3 on the first one, so now I'm gonna put the 3 on the first oscillator, right? I could have 0 here and 1 here, or I could have 3 here, 1 here, and 0 here, right? So now this is all the combinations of 3 and 1. Now I could move on to 2's, so I could have 2, 2, 0, right? Or I could have switch the second 2, so I could have 2, 0, 2, or I could have 0, 2, 2, right? And if I were to continue, then I would get the 1, 2, 1, 1, 2, 1, that's 4, or and then the combinations of these 1, 1, 2, or 2, 1, 1, that's all 4. And then of course one of them could be 4 and the other 2 is zeros. Any one of those could be the 4, so either this could be the 4 or this could be the 4. So 0, 0, 0, 0. Okay, I think that's it. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So so to answer the first question, the total number of microstates, there are 15 possible microstates. There are 15 possible microstates, and let's see if we can get this to the formula quickly. So the formula says, and I did a video with much more length and detail on how we can arrive at this formula. We can derive it, sort of. You can check out that video on combinatorics if you like. And so this formula is, let me just go straight to it, q plus n minus 1 factorial all over q factorial n minus 1 factorial. And so plugging this in for 3 oscillators and 4 energy units, we get 6 factorial divided by 4 factorial, 2 factorial. So what's this? Do the math, you get exactly 15. So this matches our table. So that means the number we got using the formula is the same as the number we got using the tables. So you can see it gets tedious with tables, but the formula can take you there quickly. Okay, the rest are very similar. So if I were to go to part B, and here we have n equal 3, q equal 5, right? We're just gonna get more. Here you can see it's probably gonna be more like 21 states, 21 possible microstates. Okay, so let's see. Usually the easiest way, the strategy to begin on these, like, start with the maximum number of Qs possible on one of the oscillators, and then bring them down one and swap the one between the other two oscillators, and then do all the combinations on that. In other words, vary the maximum number of Qs on either one of them, with the other two values going to the other two, and then keep going down by one until you run until you come to a repetitive combination which you've already done. So keep bringing them all the way down to 0. So for example, let me try to elaborate this way. Maybe this would make more sense here, where we have n equals 3 and 5. So if I were to do oscillator number 1, 2, 3, okay, and I'm gonna put the energy here. Okay, so this is what I mean. What I mean is, start with the maximum number of energies on the first oscillator. So this would be 5, and if my total number of energies is 5, then these two guys would have to take the zeros. But this 5 could be on any of the other two oscillators. So you could have a 5 here, or you could have a 5 here. In either case, this would have to be zeros, so you can so that the total could be 5. Okay, so that gets you all the microstates with one of them being 5 energy units. Then go down to 4. Now when this guy is 4, this guy could be 1 and this guy could be 0, or this guy could be 0 and this guy could be 1, and this guy being a 4, right? Then alternate the 4. Now the 4 can go to the second oscillator, and then this could be 1 and this could be 0, or this could be 0 and this could be 1. But then this 4 can also be on the third oscillator, in which case the first one can take 1 and the second one 0, or the first one 0 and the second one 1. So this runs me out of options on the 1 and 4. Then bring the total number of energy by 1. So we've done the 5, we've done the 4. Now we go down to the 3. And then if this guy is 3, then the second guy can take a 2 and the third guy can take a 1. Sorry, 0. So that's 5. Or this guy can take a 0 and this guy can take a 2. So that's all on the 3. Or this guy can take a, so now, and now vary the 3. So now these combinations could, you know, the 3 could be here and the 2 here and the 0 here, or the 3 could be here and the 0 here and the 2 here. So this is just swapping the above option. Or the third one could be the 3, in which case this could be 0 and this could be 2, or this could be 2 and this could be 0. Okay, what else? Now you could have a 3 with a 1 and 1. So this guy could be a 3 and this guy could be a 1 1, and now swap them. Of course the ones are, you cannot swap the ones because they're the same. This is the same microstate, but you could put the 3 here, in which case these two would be 1s, or you could put the 3 here, in which case these would be 1s, and here you'd run out of options on the 3 1 1. Alright, and now we'll go down to 2. So if the first guy is 2, now we've already exhausted the option. Now we start running backwards, so we have to watch for repetitions because we've already done the 2 0, the 2 3. Okay, so now, but we didn't do the 2 2. So now we could go, so the first one could be 2 2 1, or of course 2 1 2, right? And 2 2 1 2 1 2, and then the 2's could be here, and this guy can take a 1. Okay, so that's 1 2 2. Okay, what else is left? So I've done the 4, I've done the 5, so now I'm down to 1 on the first oscillator, but again I've already did the 4 and the 1. 4 1 0, I think that's it, because I've done 1 1 0. Let me see. So 0 1 4, did we already do the 0 1 4? 0, no. So now on the 4, so okay, if the first one is 0, we did the 0 5, we did 0 4 1, and we did 0, I didn't do the 0 1 4, did I? 0 4 1, I should have done that here actually. Yeah, I'm wondering why I didn't do the 0 0 1 4 0 1 4. No, 0 1 4 is here. 0 4 1 is here. 0, I think I've done them all. Yeah, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21. Yeah, I know, because the formula, I already did this before, and the formula would give you 21 states. So yeah, I ran out of them all. So you can see I start with the maximum number of energies on one of the oscillators, and then I do all the different combinations of that, and then I go down by 1 energy unit, and I repeat the same format, except I watch out for the repetitions, so I don't state one microstate more than once. So this gives me a total of 21 microstates. Okay, and then if we apply the formula here, we get you see, here we got NQ, this is 3 comma 5, so this will be 8 minus 1, 7 factorial, divided by Q factorial, which is 5 factorial, times n minus 1, 2 factorial. Okay, and then if you do the math, you indeed get 21 microstates here. Okay, so this is part B. Part C. Okay, for part C, since this is repeating, I'm not gonna do the table, it's the same thing. So I'll just use the formula on number 3. So for part C, we have n equals 3 and q equals 6, and I'm gonna get using the formula wait, part B, 3 5 and B C. Okay, so this would be let's see, 3, so we're gonna get 3 6. Let me just use the formula on this. So we would get 6 plus 3 minus 1 factorial divided by 6 factorial times 3 minus 1 factorial. So this would be 8 factorial over 6 factorial times 2 factorial. 8 minus 1, 9, yeah, divided by second q factorial, yeah, q is 6. So 6 factorial times 2 factorial, so we would get 28, which is what a table would give you. For D, G is 4 and 2. Okay, maybe we can do the table on this one, because on this one there aren't that many. So n equal 4. So here we started, originally we fixed n and we started going up on the number of energy units. Here we are going down on q and we are raising n, the number of oscillators. And so if we do that, we will get, let's see, this is q equal 2, so oscillator should be double L here, 1, 2, 3, and the energy goes here. Oh, 4. I have 4 oscillators. Actually, bring this a bit closer. So I can stay on the page. Okay, so again, the first one could be 2 and the rest 0, so all the energy units could be on the first one, and then I can make this 2 anywhere on the second 3. So this could be 2, or this could be 2, or this could be 2, and the rest zeros. It's sort of like a matrix with 2 on the diagonal, right? Okay, so that exhausts the 2 option. Now one of them could be 1. Right, so one of them could be 1, but then if that's the case, someone else would have to take a 1. So either this could be a 1 and the rest zeros, or this could be a 1 and the other 2 zeros, with this being a 1, or the third one could be a 1. Uh, 0, 0, 1, right? Now the first one could be a 0, correct? So let's change color. The first one could be a 0, this could be a 1, 1, 0, right? And the first one could be a 0, but then I could make the second and fourth one 1s and the middle one 0. Or the first one could also be a 0, but the third and the fourth be a 1, and this guy would be a 0. So that exhausts my options on the on the ones. Are there any other ways you can think of distributing 2 energy levels on these? I don't think so. We've exhausted all the options. So if you count these, you would get a total number of 10 possible microstates. So 10 possible microstates. And then let's apply the formula. We should get the same with the formula. So this is 4, 2, and we would get 2 plus 4 minus 1 factorial over q factorial 2 factorial times n minus 1 factorial 4 minus 1 factorial. And the answer here, if you do the math, you would get 10 microstates. Okay, number E is the same thing. I won't do the table, I'll just do it using the formula. So here n is 4, q is 3, just repetition. So possible microstates for 3 we've got q plus n, so that's 7, 3 plus 4 minus 1 factorial divided by q factorial 3 factorial times n minus 1 factorial 4 minus 1 factorial. So we would get, one moment, I haven't punched this in yet. Could get 20 microstates. Okay, let's do the last two cases, F and G, just because they kind of show some limiting behavior. They're sort of important. So let's do F. So here we have n equal 1, so we have only one oscillator, and Q could be anything. Okay, well, if Q could be anything, then there should only be one microstate, because there's only one oscillator, right? And that one oscillator could be it could be any of the energy state at one time. So there's no multiplicity. There's just only one microstate in each energy level that this one oscillator will take, whatever Q is. And so just reasoning alone would tell us that there's only one possible microstate, one possible microstate. But let's use the formula and see what we get. So here we have n 1q, so this should be q plus n, so minus 1, so q plus 1 minus 1 factorial divided by q factorial times n minus 1 factorial, so that's 1 minus 1 factorial. So we get q factorial over q factorial 0 factorial. Now keep in mind that 0 factorial is equal to 1, so these two are the same, so we get 1. So for a single oscillator, there's only one microstate possible. Okay, the last one, G. Now the other way around. Now we have any number of oscillators, so this is anything, n, big N, and there's only one possible energy level available, right? So in this case, you're gonna get n possible microstates, right? Because you know, if n is 5, then all the oscillators will have one energy level. One of them will have one energy level, and the rest will be zeros. But then you can alternate this one energy level on either one of those 5, so you're gonna get 5 different microstates. So in other words, the number of microstates will be capital N. And you know, if you do the table, like let's say, let's actually try to do it quickly. 1, 2, 3, 4, all the way to N. Okay, and let's say we have Q equal 1, and this is energy here, right? Well, clearly, if the first guy is 1, the rest of the guys will have to be 0 all the way to N. And this is one possible microstate, right? But then the second one could be 1, and the rest could be zeros, right? And then the third one could be 1, and everyone else would be zeros, right? And then I can alternate this 1 into n different oscillators, and any one of these n different oscillators could be the 1, and therefore I would have n microstates for Q equal 1, because it would keep going down and zeros all the way till I get to 1 being here, right? Sorry, this is supposed to be a 0 here. And so I would get 1 on the diagonal and 0 everywhere else. Well, this is an n by n matrix, right? And the possible number of microstates would be n. And let's use the formula just to confirm it. So nq, so this would be q plus n minus 1 factorial over so we said that q is 1, so let's just put 1 here, and over q factorial, which is 1 factorial, times n minus 1 factorial, so this would be n factorial over 1 factorial is just 1, and this is n minus 1 factorial. Now n factorial is 1 times 2 times 3 all the way to n, so we cross the n minus 1 and we get all the way to n, and n minus 1 factorial is 1, 2, 3 all the way to n minus 1. We can see that all the terms up to n minus 1 cancel, and the final answer would be what's remaining on top is just n, and so as expected we would get n microstates. So the formula shows that you get the same exact number of microstates as the one using the table. I hope this question does clarify how to set up these Einstein solids with a given value of n and q and figure out the possible number of microstates. This concludes the question.